Hello, welcome to Functional Bar. My name is Charles, and in today's video, we'll be discussing functions. We'll talk about how functions are similar to math functions in Haskell, which is different from other languages. So for those of you who've got some experience in other languages, we'll quickly review what that means. For those of you who don't know what a function is, it's still good to pay attention, but don't worry too much if it doesn't make much sense. Then we're going to talk about what a function actually is, how we can think about that, and it's a math function, so I'm mostly going to rely on everyone remembering what they learned in math class. Then we'll have to talk about types, and that's because it's very difficult to talk about functions in Haskell without also talking about types. Types are central to Haskell programming, so it's good to start learning about them now, even if we just learn a couple of them. Along with the types, we'll have to learn, since we'll be discussing types other than string, we'll have to learn how to turn types into strings. And that's real easy. It's just a function call. Then we'll move on to how to actually make a function and how to use a function. Finally, we'll wrap things up with some suggestions for practice. And like always, or like last video, I'll review one of those for you. But unlike the last video, I'm going to leave these last three for you to do on your own, should you choose to. So let's get started. In Haskell, functions are just like the functions you learned in math class, in algebra especially. Now this is different from most programming languages. In most programming languages, especially procedural and object-oriented programming languages, functions have something called a side effect. That is, they change something outside of themselves, or they read something outside of themselves. In object-oriented programming, often the functions will access something inside that object. The other thing that Haskell functions require is referential transparency. That's a big word. It just means that when you call a function with one set of arguments, you always get the same result back. This is perfectly intuitive. For instance, if you add 1 and 1, you always get 2. You never get something different unless you're changing your base. Your numeric base, which is a programmer joke, I guess. Other languages often allow side effects or even encourage them. Object-oriented programming tries to keep the side effects constrained into objects for the most part. And they also allow for referentially opaque functions. That is a function where 1 and 1 does not necessarily equal 2. A common example of this is the random function. It's referentially opaque. It looks referentially opaque. Under the hood, it's actually generally a pure function. So now, what is a function? So we've talked a little bit about how they're different because I expect most people are coming into this from a different language or some experience from a different language. So what is an actual function for those of you who don't know yet? Well, it's just like I said, it's just add. It's exactly like what you learned. In Haskell, a function is exactly like what you learned in your algebra class, except we can do a lot more with it than you probably did in math classes. They transform values. The most basic definition for function is that it transforms a value. In computer science, is that it transforms a value. So if you give a function 1 and 1, it transforms 1 and 1 into 2. It could transform 1 by just adding 2 to it, and then you get 3. And often, we'll take like an integer and turn it into a string is something else. And again, it's very difficult to do this without referencing types, as I just did. More formally, and this is not quite a formal mathematical definition, but I think it's getting close. A function maps a value from one set into a different set. Now, a set is just a collection of objects, and that's not objects as in object-oriented programming. That's object as in thing. It's a mathematical concept, not a programming concept in this sense. So it will take a thing from one set, and it will map it to another thing. So if you have a set of numbers and a set of fruit, it could map the number 1 to apple and the number 2 to an orange. It's a bit of a contrived example, but you've probably seen teachers in the past draw these diagrams on the board with big ovals and some numbers in one and maybe letters in another and arrows drawn between them to help explain functions. Finally, since this is a programming talk, we're going to talk about how a programmer might think of functions. And this is often what I think about them, or how I tend to think about them. A function maps a value from one type to a potentially different type. Now, types are not sets, but types are related to sets. They have sort of the same characteristics in many senses. But then what is a type? We're just going to briefly talk about types here. Type theory, especially in Haskell, is very involved. You can think of a type, and in fact, if you were, I started as a C programmer, where types certainly had additional meanings, but one of the fundamental meanings of a type was how to interpret a set of bits we fetched out of RAM or off the hard drive, because everything's binary. It's like 0, 1, 0, 1, 1, 1, 0, 0, etc. So the compiler and the program it produces needs to know how to interpret a chunk of bits from RAM. It also needs to know how many bytes to fetch from RAM. And types tell it that. So the compiler can figure that out. Now, type theory, in Haskell especially, has a number of other benefits, especially in terms of error detection. Because if our types don't match up, then there's probably an error. There's almost certainly an error. Strings and ints are examples of types. So we're going to work mostly with strings and ints. A string is just a thing that we can print to the console with Perth-Sterlin. It's got when we write it literal, it's got the double quotes around it, like we saw in Hello World. We use string literals a lot there. Ints are just numbers. Haskell also has something called an integer type. The integer type can represent any integer. Now remember, an integer is -1, -0, 1, 2, 3, -100, +156. That's an integer. Sometimes they're called whole numbers plus negative numbers. It's a mathematical set of integers. In Haskell, integer is a type that allows any one of those numbers. But the set of integers is infinite, and so the integer type in Haskell, our RAM isn't infinite, but the integer type in Haskell will let us represent numbers up to the capacity of the RAM on our machine, or memory in our machine. Int, on the other hand, is a 64-bit integer, which means we can get numbers up to as large as 64 bits. Now that's hedging things a bit. How we encode things actually means we can't get 2 to the 64th because we have to represent negatives. The takeaway here is that int gets us a very big number. It's like 2 to the 27th, somewhere around there, or 9 quintillion. It's very, very large. For all practical purposes, outside of scientific applications like in astronomy, perhaps genetics, that sort of thing, an int is going to be perfectly good for your needs and much, much faster than the integer type. The integer type has to do a lot of extra stuff in order to represent those very large numbers. All right, so let's get started with some practical work here on how we make a function. And I'm going to start by making a new project. I'm just going to call this Haskell-functions. You can call it whatever you like. And this is our basic new stack program. So we can do stack run, and we'll see that I'm not in the correct directory. So we can do stack run, and then we see the expected output of the default stack program, some func. So let's open that program up, the main up. Remember, app is a directory that main lives in. So this is the basic program. And as always, I'm going to make it look like what I want it to look like. Our basic Hello World program. I'm going to run it. And we're going to see Hello World down here. My image shouldn't be in your way, but I'm going to bring this up just in case. So how do we make a function? Let's make a simple function called hello message. It takes a string and it gives us another string. This is Our type specification, now we read this, is the arrow means a function. If you see a type specification without an arrow, that's not a function. Now we look down here, main is not a function. Now if that's baffling to you, you can relax a little bit. It turns into a function later. The compiler will ultimately do something special with main because main is always a special function in other languages. The program entry point is always special, and Haskell is no different. But main is not really a function. It's the IO monad. Eventually, that's going to turn into a function. But that's under the hood. We never deal with that. So for our hello message here, we just take a string and we return a string. And for this one, we're just going to call it name. For our parameter, a parameter is a special kind of variable. I'm going to finish writing this up really fast. A parameter is a special kind of variable, one that only lasts as long as the function invocation. Now we see here this equal sign, and sometimes the Haskell compiler will produce error messages that talk about an equation. Well, that's because we have an equal sign here, and as we learned in math, if there's an equal sign, there's an equation, because hello world or hello message, space name with the argument name, equals is always equivalent to this. And what this does, we have our string. This should look awful familiar. We did something very similar in the last video. The string hello concatenated. Remember, we glue strings together by concatenation. We do not add strings together. We concatenate strings together. So the string hello concatenated with a white space, a string for the white space, concatenated with our parameter. And this is going to be an argument later when we evaluate it. So we're going to put name, the argument we take in here, this name, and this name are going to be the same. Now let me write this just a little bit different. Often you'll see functions written all in one line like this. This is 100% valid. When the functions get longer, we'll have multiple lines like this. For what I'm going to do in a minute, this is going to make things a bit easier though. So let's use that function. So that's how we make the function. We have our type specification line, and it has the double colons. So hello message space double colon space this string pointy arrow string. The arrow comes from mathematics again. Haskell is a very mathematical language. It was developed from the lambda calculus. Mathematicians and logicians and whatnot have worked very hard on this. And now, of course, compiler developers and Haskell language developers are still working very hard on this. But a lot of this notation comes from earlier mathematical notation where an arrow actually means a function. So in Haskell, the arrow means a function. So we have string. We map a string onto a string or into a string. I'm sorry, this would be onto. Don't worry, it doesn't make that difference. So now to use that, we just type the name of the function. Then we have to give it an argument. And remember, we have to put our parentheses here because putStrlen is a function, and we need the order of operations mean that it's going to try to call putStrlen with hello message, the function hello message, as an argument, instead of what hello message evaluates to, instead of the return of hello message. So what we want instead is for it to give us to print the return of hello message. So we put the parens around it. Save that off. Now let's run our program again. And we see it says hello Charles, as we would expect. Let's change that. It's always good to change things just to make sure that they work. Indeed, we see hello Jane showed up instead of hello Charles. Now, how does that actually work? Let's walk through this, and that's why I wrote this in one line. So the compiler sees hello message Jane. It says, I know hello message. Hello message is a function, and it takes one argument. It accepts one argument, and right now that's the string literal Jane. So what it does, I'm going to write it up top. I think it'll look a little easier. or look a little better, easier to read. So the first thing we do is we replace all of the occurrences of name with Jane. So now we see hello message Jane is equal to string, concatenate with string, concatenate with string. So we've eliminated the variables. We've eliminated the parameter. We've reduced it to an easier to work with form. And now the compiler is like, oh, I know how to deal with this now. Before we couldn't reduce the concatenation so much because we had a variable in it. Now we don't have a variable in it or parameter. Oops. So we concatenate everything together. So we've applied this function because this is a function. It's an operator. It's an inline function, and it takes two arguments, as we would expect, the hello and the white space here, and it concatenates all of these together into hello Jane. So now the compilers reduce this down to hello message Jane equals hello Jane. And I said, okay, I know the answer now. Hello message Jane is always equal to the string hello Jane. Always. It never changes. That's what referential transparency is about. It's a very important property in Haskell. So it can take a note, and it takes a memo. It memoizes this, and it'll remember it for a while. Maybe not forever, but it'll remember it for a long time. So it doesn't have to do that expensive computation again the next time we call hello message with Jane. Now, the steps I've taken here don't necessarily happen at runtime. I don't want you thinking that at runtime, we're actually doing all these different reductions. A lot of this happens at compile time. And then, of course, it gets compiled into machine code, which does something completely different, but still has the same meaning. So when we get down here, we see hello message. The compiler knows hello message Jane is equal to hello Jane. So it replaces it with hello Jane. And now it evaluates the contents of our parentheses. Remember, inner, outer, left to right, that thing for order of operations. So hello Jane, we can just get rid of the parentheses now because we evaluate the string hello Jane in parentheses. It's just a string hello Jane. And now we have Putzerlin hello Jane. So this is how the program evaluates conceptually. So you can think of it as working just like that. And it's going to get you a long, long ways in terms of understanding how these programs work. Now, again, it doesn't mean that's what actually happens under the hood. The Haskell compiler, because all of this is based on math, well understood math, the Haskell compiler is able to make a lot of optimizations. So it can do things up front at compile time that aren't possible necessarily in other languages. So it can execute quickly, even though it's a really high level language. All right, so now let's look at another type, the integer type. Let's look at increment. This just adds 1 to everything, a function that adds 1 to everything. So it takes an int and it returns an int. And now the argument to increment, the parameter to increment, it doesn't really make any difference. The name doesn't make any difference. It's just, we just need it there. It's some placeholder, right? X equaled x plus x would work, but let's do x plus 1 because that's what the function we're writing is, right? So it takes an int as a parameter. We've named that parameter x. So inside the function, the variable name for that parameter name is x. So it looks and works just like a variable inside that function, and x plus 1. So we add 1 to x, and that's what gets returned. It's another integer. Now I told you, now for ints, we can't just print an int. So if I do this, we're going to get an error. It's going to say, I don't know how to print an integer. So Putzerlin increment, indeed, cannot match type int with bracket char. Bracket char is string, and it's just, they're the same thing. They're exactly the same thing. They're just an alias for one another. A string is a list of chars, so don't worry about a list very much. Just focus on a string, being the string literal, the thing that we put human language in. And it says, I expected a string, but what I actually got was an int for Putzerlin on increment here. Now, how do we fix that? in almost all cases with put_ln, or in fact, anywhere you're expecting a string, we can use another function called show, and that's just always going to be there. So because show now has to be called against the int, we show increment 1. So we do increment 1, and then we show whatever the result was, and show turns it into a string. So it's very accurate to call it show in this sense, where we're printing stuff onto the console. We want to show what that means, and so that it's going to turn it into a string for us. So let's save that off and let's run it again. And we have 2, because when we add 1 to 2, we get, when we add 1 to 1, we get 2. So let's work through that again, sort of like the compiler is going to do, like the program's going to work. So we replace all of our x's by the argument, the value for the parameter, right? So it's 1, so we've replaced all the x's by 1. We see increment 1 is equal to 1 plus 1. Well, this should be very, very easy now, because we know what 1 plus 1 is. 1 plus 1 is 2. So again, the compiler says, oh, okay, because of referential transparency, the fact that for all functions, if we give it an argument, it's always going to give us the same value for that argument, always. So we say, okay, now I know the answer. I'm going to remember that. I'm going to memorize that. And this is something you don't necessarily have to know about for all functions. It happens under the hood automatically all the time. But sometimes you'll come in and say, oh my gosh, that function is so long and complicated. How is this ever going to be efficient? Well, one, you shouldn't worry about it until runtime. Until you actually have performance problems. And two, with a Haskell compiler, it's probably been optimized a lot anyway. So, but at any rate, we've now memoized increment 1 is equal to 2. So we know the answer to that. And we come down here and we say, oh, show increment 1. Well, that's 2. And it's an integer 2. So now it's show 2. And then show 2 gets evaluated. The compiler knows how to do that. Show is complex. We're not going to talk about show for a while. We can make our own show for our own types, but we're not going to do that for a long time. So show 2 turns into just the string 2, because it's what show does. It takes a type and it turns it into a string. So now, how do we do the thing? We have the string 2 inside parentheses. What does that mean? We've evaluated that. That just turns into 2. Now we have put_ln of 2, and we know exactly what that means. We know how to do it. So that's, again, not necessarily what happens at runtime, but it's the steps that we go through when evaluating our functions, or the compiler goes through when evaluating our functions. All right, let's talk about the ID function real fast. It'll be our last unary function. Unary meaning it takes a single argument, something called arity. This takes one argument and gives us a return. So let's talk about the ID function. I'm going to call this int ID. There is a function called ID, and it works the same way, but it works for everything. And since we're not ready to talk about how to make a function generic or with parameterized types, we're going to focus on int ID right now to explain that. Now, x equals x. The ID function is, one, very simple, and so it's very useful for study. Two, it crops up sometimes that this is actually really useful. We get into some stuff, it'll just appear to be essentially useless for a while. But when we get into more complex things, you'll be reading along and you'll see some functions are just defined in terms of ID. And so you need to know that ID is a function. So here we have int ID. So we can do ID of 5. Right? It's the same thing otherwise. Just ID of 5, int ID. Whatever value we put in gets returned. So we should see the number 5 for output. And instead we see that I have a syntax error. Again, this is a compiler helping us find bugs. So when we're finished with our program, our users don't have bugs. Oops. and I talk so much about real ID. We still had 5, but we had a warning. We'll come back to that warning here in just a minute. Okay, int ID of 5. And you see we didn't get warnings this time. So what was that warning with ID? ID is an actual function. ID takes any kind of type. Now remember I said earlier that there's lots of different kinds of number types in Haskell. In particular, there's an int and an integer. And we want to use int because it's a little bit faster all the time. And we want to avoid integer unless there's a need to use integer. Well, because integer is more general, the compiler said there's no decimal point, so it's an integer of some sort. I don't know how big you expect it to get. I'm going to make it an integer. So it gave us a solution that will work, but it's a solution that's not as great. And so that's why it gave us this warning. And it says, show, I don't know what this is, because when we just type 5 by itself, it just doesn't know what that means. Is it an int or an integer? So it gives us this warning. And show has to know what it takes. Now, when we did int ID, that didn't happen. And the reason it didn't happen for int ID is int ID only takes an int and only returns an int. So show knows exactly what that is. So let's trace through this real fast. We call int ID of 5. So int ID 5, we replace all of our x's with the value of the argument 5. And we don't do anything else. This is such a simple function. That's all we have to do. Int ID of 5 is equal to 5. We can take our note. Remember, we memorize that. We memoize that. And so we can just replace this with 5. And we have 5 in parens. So we evaluate that. And the parens go away because there's only one value there. There's only one thing in the parens. Then we have show of 5. And we know what show of 5 turns into. The compiler does that for us. Clever people have written this for us. So it turns it into the string 5. And then we evaluate that. And then the parens go away because there's only one thing in the parens. So the parens just go away. That's Putsterlin 5, so Putsterlin has a string at once. Now I'm going to show you a couple of different ways to do this. Just leave it there. This name here could be anything we want. It could be Y, it could be A, so I'll use A real fast. Right? The variable name doesn't matter. There are some rules, but so long as you start with a letter, and you should start function names, parameter names, and variable names with a lowercase letter, and don't have any funny characters in it, it's always going to work just fine. And we're going to stack run, and we see 12 shows up just fine. All we did is we changed the name, or the spelling really, of the parameter from X to A. Now let's quick review. We could do it this way with a variable. 14. So this is still an int. Remember, we can make variables a couple of different ways. Just quick review of those variables. This might be more legible. I often see people put lots of stuff all in one line. And so long as that's less than 80 characters, generally that's just fine. And it depends on where you're working, how long lines can get. But you should look at it and say, which do I think is easier to read? And here, this R for result, I didn't have a better name for it. But in a real program, you'll often have better names for it. So we can run that, and we're going to see 14. Oops. When I save it and run it, you're going to see 14. So we see 14 here. And don't forget, we have the other way to make our variables in Haskell. We'll say int ID 8. Both are perfectly fine. You run with the one, you use the one that you think is most readable. So we see it says 8. All right. So that's it for our functions. How to make a function, how to use a function. We also reviewed a few functions. And just real fast, if you need ID, don't write your own ID, just use ID. And that's the function you should use. Oh, before we continue, I forgot because, well, we'll get here. So write hello world using a function hello message. Well, I didn't do a good job of defining hello message, and that's because it doesn't make much difference. We just wanted to use hello world with a message, and this is going to be awful similar, so we'll, with a function, I'm sorry, hello world with a function. So here's our basic hello world. And this is what we did a minute ago, right? So this is all hello world with a message is, and then you have to use it. And what I would encourage you to do at home is find a different way to write a function. Write this function yourself, of course, like we did it here, and then just find ways to change it around some. Maybe make a different function that does something a little bit different. Maybe it computes the entire hello message. You can make functions that call functions. That is absolutely 100% correct and a really core feature of programming in any language that supports functions. See, this is hello world. So that's all we do for that exercise. And then we can change around as much as we want, try to come up with different ways to break this into functions. Hello world is a really simple program. It just says hello something on the console. The only thing I want to caution you about is to only have one put strlen. You can have your let, whatever goes there, in to make a variable and then print your variable, or you could use the where to make your variable and maybe use the function call with the variable just to get some practice doing that. That would be really useful. But just only have one put strlen. And the reason is because of Haskell. We'll get to how to do more than one put strlen in our main later. And then, so that's hello world, the hello world function using a function hello message. That's what that looks like. Now subtract, multiply, and divide. I'm going to write add for you really fast. And subtract, multiply, and divide should follow naturally from add. So add is an int, turns to an int. Now it doesn't have to be int. In real programs, we do not write our own add function. Actually, I'm going to do add int just to make sure I don't have a name collision. In real programs, we don't write our own add function typically. We'll use built-in library functions. And in fact, we're going to use a built-in Haskell operator for add. The plus sign is an operator, which is a function. It's just a special function. It's called infix or inline. And it goes like between the two arguments instead of otherwise around. But that makes it look very natural to pretty much everyone. We know exactly what x plus y means. So add int x and y. All right. So we just call, just like we did all of our other functions, it returns an, oops, sorry. Returns an int. I got my signature wrong. So it takes an int, takes an int, takes two ints, and it returns an int. So we get add int 4, 5, and that's going to give us 9 after I save it. It does give us 9. And we can extend this if we wanted a function that takes 3 integers, we just put another integer here. And keep going, keep going, keep going. Now, the reason this makes sense is because what actually happens is this is a function, right? Which then executes and it returns an integer, and then that becomes a function which accepts an integer and returns an int. So let's do add int prime is equal to add int x. Sorry, y to keep up with my nomenclature here. we should still have x and y. I don't know, this is 6. So if add int, or regular add int, it just adds. And then it's conceptually going to evaluate into a function which is add int 6 partially applied, right? If we do add int 6, and that's going to accept the y argument and then return an integer. And if none of that makes any sense whatsoever, don't worry about it at all. It's just that we have a function that returns a function. This is a normal thing in Haskell, and that's why these arrows make sense. And I'm sorry, I probably should not have delved down in that rabbit hole. I didn't mean to. I stumbled into it accidentally. So this is an add int. We have x and y's and x plus y for our parameters. Now, because that now starts to look a little bit gnarly down there, I'm going to also write this with a variable like we did a minute ago. Right? So we can run that again and see that it works. This might make it more clear to see. I don't know how I'd write it in a real program. Maybe either way. It just sort of depends. And then we can evaluate this. We'll go quickly through the evaluation. Add int 4, 5. Replace all the x's by 4, all the y's by 5. Forgot the plus sign. And so then we replace r by 9 and replace show r, etc., just like we did before. The only difference is we now have an extra parameter, y. And again, because addition doesn't really have, I think addition actually might have special names for it if we look it up on Wikipedia or whatever, but there's nothing particularly meaningful about it because order doesn't matter. So for our for the suggested exercises at home, some things to do at home for practice, you can make a subtract int or sub int for subtract. And it's going to have the same signature, multiply, and a divide. And so multiply works just like subtract is just a minus sign, multiply is a star sign, and div is the forward slash. And that's how you get those to work. And so that is it for the suggestions for practice. And of course, you can just invent any sort of thing that you like. I would suggest you stick to strings and ints and not get beyond that for now. Of course, you can use any type you want, but they start to get a little bit more complex the further you get into it. And right now we're really focused on functions, not types. We'll introduce types slowly as we move forward in the video series, different types and how to make our own types. So to stick with the ints and strings for now is my suggestion. It's a soft suggestion. If you want, you can jump into all sorts of other stuff and do whatever you want that helps you learn, and especially helps you learn functions. And then maybe write a function that just computes the string that we're going to print, like the hello world of the function, and then continue with our little simple calculator examples with subtract, multiply, divide. And so let's quickly review what we talked about in our video, and then we'll be done. So we talked about how functions in Haskell are like math functions. We learned some really big words that are very specific about what that means. In Haskell functions, anytime you have a call a function with some set of arguments, the same set of arguments, you always get the same return value that never changes, and the functions never read or write outside of the function. And that's different from other languages. We talked about how a function transforms values, or maps values from one set to another, or maps values from one type to a potentially different type. So we talked about how functions can do all of those things, and those are reasonably good definitions for functions. Actually, the second one is a math definition for function, or very close to it. And I'm hoping that you already learned that in algebra class at some point. Now, what are types? We talked about them just a little bit. Again, string and int, they're the kind or the sort of thing, the things that we can put into our function and the things we can get out of our function. And compilers often use types to learn or to know how to put things in memory and read things from memory. Programmers often use types to know what a function does. Then we talked about how to make a function and how to use a function, and reviewed some things for practice. We also talked about a few different kinds of functions where we're talking about making and using a function. But that's all good. So that is it for today's video. As always, questions and comments are welcome. Thank you for watching. Please click like and subscribe, and have a great day.